Well, there are different types of solutions. The most common ones we talk about are aqueous solutions. In an aqueous solution, water is the solvent. The solute could be a gas, a liquid, or a solid that's dissolved. And so here we have examples of some different types of solutions. If you have the solvent being a liquid, you can have a gas dissolved in that. Club soda is carbon dioxide dissolved in water. Liquid, vodka is a solution of ethanol and water. They mix together evenly. A solid dissolved in water would be something like seawater, salt dissolved in water. You can also have solutions where both the solute and the solvent are a solid. An example of this is a metal alloy. Alloys are not compounds. They are mixtures. They're actually solutions. So brass is a mixture of copper and zinc, a solution. And gases make solutions with other gases very easily. The air that we're breathing is a solution of gases. It's mostly oxygen and nitrogen, but it's also got carbon dioxide and argon and some other things in there. Solubility is the term we use to describe how much substance, how much solute, there's a typo. We use that to describe how much substance, how much solute will dissolve in a given amount of solvent. So if you take a drinking glass of water at home and you put some salt in it and stir it, it'll dissolve, right? If you keep doing that, eventually you'll come to a point where no more will dissolve. And that's the solubility. It's how much will dissolve in a given amount of solvent. Well, let's talk more about this tendency towards mixing. We've discussed over the semester many things where stuff happens to lower the potential energy, right? Many physical systems tend toward lowering potential energy. Formation of a solution doesn't necessarily lower the potential energy. If we look at two gases, neon gas and argon gas, and we allow them to mix, the temperature's the same, the volume's the same, the pressure's the same, did the mixing do anything to their potential energy? No, it didn't affect their potential energy. So why are they mixing then? Well, there are other things involved here. One of them is entropy. Entropy is a concept that can be a little difficult to understand. It's a measure of energy randomization or energy dispersal in a system. So when two ideal gases mix, the kinetic energy of each gas becomes spread out over a larger volume. That results in an increase in entropy. I often think of entropy as being messiness, okay? And if you were all children at some point in your life, some of you very recently, or if you have children, you know that a child's room tends to get messy, right? You may find that with your own living space. You know, it just tends to get messy, right? The leaves that fall off a tree, do they fall into neat piles? No. They were neatly arranged when they were on the tree, weren't they? They were attached to the little branches in a particular way. When they come off, they become all messy. Take a brand new deck of playing cards. All the suits are all numbered in order, and play 52 card pickup and flick them on the floor. They get all messed up, don't they? That's entropy. That's an increase in disorder. But specifically, it's an increase in disorder of the energy or a spread of the energy. So the reason that substances mix is due to this pervasive tendency for energy to spread out whenever it is not restrained from doing so. So the two ideal gases mix because the kinetic energy of each of them can spread out over a larger volume. This also explains why thermal energy flows from a hot object to a cold one. The thermal energy is spreading out, and that causes an increase in entropy. Now, intermolecular forces have an effect on whether a solution forms or does not form. They can promote the formation of a solution or they can prevent it. And we've talked about intermolecular forces. If we look at heptane and pentane, these both have dispersion forces. And so these are going to be attracted to each other. Acetone and chloroform both have dipole-dipole forces. Ethanol and water both have hydrogen bonding as their strongest intermolecular force. And then between an ion like sodium and water, we have ion dipole forces. So in a solution, we have forces between the different components. We have interactions between the individual solvent molecules. We have interactions between the solute molecules. And then we also have interactions between the solvent and the solute. So there's 3 different types of interactions. So if we have strong interactions between the solvent and the solute, those are stronger than the interactions that the solvent has with itself and the solute has with itself, then a solution will form. If the solvent-solute interactions are similar in strength to those of the solvent-solvent and solute-solute interactions, a solution will form. But if the solvent-solute interactions are very weak, a solution will not form. So I think I told you my analogy of Japanese and Swedish people in a room, and the Swedish people only speaking Swedish and the Japanese people only speaking Japanese. Okay, the interaction between a Japanese person and a Swedish person is going to be very weak if they cannot communicate in the same language. And so the people are not going to mix, they're not going to form a solution. They're going to stay in each on their own side of the room, or at least in groups, right? Because the interactions between different Japanese people that all speak Japanese are strong relative to their interactions with the Swedish people. Does that make sense? If we get comparable interactions of the Swedish and Japanese people compared to the Swedish people with themselves and the Japanese people with themselves, then things are going to mingle around. Or if the interactions between the opposite kinds of people are stronger than those within, we're also going to have mixing in a solutional form. Does that make sense? Not really. There's some people like it, some people don't. Pardon me?
Interpreter is equal and bilingual is...
That's good. I like that. Yeah. So here, the interpreter, you could have an interpreter or you could have bilingual people, and so then they're going to interact more easily. If we have very weak interactions between the solvent and the solute, the gain in entropy from things spreading out doesn't make up for the energy loss caused by breaking the strong interactions between the solvent molecules and between the solute molecules. Let's see if we'll have a picture coming up. No, I don't have a good picture. We'll have to go back to this picture. So let's say that this is water and that is something dissolved in the water. So the water molecules are attracted to each other very strongly, right? In order for this red substance to mix in with the water, the interactions, the hydrogen bonding between water molecules has to be broken. Does that make sense? If that is not replaced with a similar strength interaction between the solvent, the water, and the solute, then it's not going to happen. If we have really strong interactions between the solute particles, it's going to be hard to get them to separate. It's a little bit like cliques in social settings, right? You get a clique of people, there's this small group, and they are just so into themselves, right? They just don't even pay any attention to anybody around them. At the party, they just get together and they talk to themselves, they ignore everybody else. The interactions between them are very strong, and you just can't pry them apart. So entropy, the spread of energy by things mixing and spreading out, is one factor. That is increasing as, that's, where am I going with this? That's increasing as things mix and form a solution. But in order for that to happen and have things mix, we have to first overcome the solvent-solvent interactions and the solute-solute interactions. And they need to be replaced with something at least similar. The increase in entropy from the mixing is why we'll get mixing even if this interaction is only similar. It doesn't have to be stronger because the entropy increase will take care of the rest of it. So this is just a little bit more involved explanation than what we talked about in the previous chapter when we said that like dissolves like. And so we should be able to answer questions like this. Determine whether each compound is soluble in hexane. Well, what's hexane? It's a hydrocarbon with 6 carbons, right? We should know that. 1, 2, 3, 4, 5, 6. And the only other element in there is hydrogen. And we'll get enough hydrogens in here to give each carbon 4 bonds. Is this going to be a polar molecule or nonpolar? This is nonpolar. Remember, I asked you to remember that carbon-hydrogen bonds themselves are considered nonpolar. So here we have a nice symmetrical molecule. There's no lone pairs anywhere. And all of the bonds are nonpolar. This is a nonpolar substance. The interactions between hexane molecules are dispersion forces. So pretty weak. Here we've got water. What kind of intermolecular forces does water have? Hydrogen bonding is the strongest one. So we've got hydrogen bonding between the water molecules. We've got dispersion forces between the hexane molecules. Are we going to have strong interactions between water molecules and hexane molecules? No. The hexane can only do dispersion forces. Now, water has dispersion forces, but the interaction between the nonpolar hexane and the polar hydrogen bonding water is going to be much weaker than the interactions between the water molecules themselves. And so, will a solution form? No. So water and hexane are not soluble. How about ammonia? Nope, not soluble. What kind of bonding intermolecular forces does this have? Hydrogen bonding again. Very similar to the water. Would the water and the ammonia mix together nicely? Oh yeah. Because the hydrogen bonding interactions between a water molecule and an ammonia molecule are going to be similar in strength to those between individual ammonia molecules or between water molecules. So ammonia is also not soluble in hexane. How about propane? Yeah. Here we have another nonpolar molecule. It's got dispersion forces. This has dispersion forces. Propane and hexane will interact via dispersion forces. And those will be similar in strength to the dispersion forces between the propane molecules and between the hexane molecules. And so this will be soluble. How about hydrogen chloride? Is this polar or nonpolar? It's polar. So what kind of bonding, intermolecular forces does it have? Dipole-dipole forces. The dipole-dipole forces between the hydrogen chloride molecules are stronger than the dispersion forces between the hexane molecules and stronger between the dispersion force interactions between HCl and the hexane. And so this is also not soluble. Does that make sense?